Next up, we have Jeff Danciger telling us about geometric structures on manifolds.
Okay, thank you, Tengrin. It's wonderful to have the opportunity to speak to everyone. So I'm going to talk about geometric structures on manifolds, and while that can mean a lot of things, the word geometry is, pretty vague. But to make it more specific, let me say this topic is really what I'm talking about is really called locally homogeneous geometric structures on manifolds. And I meant to put some references. Okay. Yeah. So, so a common reference for this stuff, at least some of the basics, is Thurston's notes, the geometry and topology of three manifolds. That's Thurston. And chapter 3 specifically. You can find this on the MSRI website. There's also notes on notes of Thurston, which is by Canary, Epstein, and Green. So once you read this and decide you're confused about some things, you go to this, and they will explain those things. And then there's a very nice survey by Bill Goldman called Locally Homogeneous Geometric Manifolds. Which is a paper from Bill's ICM talk on this subject, and it's very nice. It's a very nice survey. Okay, great. So, just as a vague overview, sort of two things I'll be talking about. There are these geometric structures, which are so the type of structure will be indicated by a geometry, GX. And to each of those things, so a GX structure on a manifold M, let's say, to each of those things will be associated a representation of the fundamental group of M into G, called its holonomy representation. So the entire theme of this course and a lot of what sort of the various researchers, that are part of the GEAR network are interested in is the connection between these two objects. How can I tell, for example, about properties of a geometric structure by understanding properties of its holonomy representation? So what are the connections there? And also, if I'm interested in just representations of discrete groups and Lie groups, can I find a way to associate to those nice geometric structures on manifolds where I can see the properties of the representations reflected in the geometry of the geometric structure? So that's kind of that's the theme we're headed for. So, here's an outline. There'll be 4 parts, 2 today and 2 on Wednesday. So today we'll be primarily concerned with just introducing GX structures and the basic theory, complete GX structures with some nice examples. And then on Wednesday we'll go to a topic that's more specific, convexity in hyperbolic geometry. And then I'll explain an attempt at trying to use a convexity notion to study representations in higher rank Lie groups. All right. Are there any questions before we get started? Okay. Okay, so what's a geometric structure on a manifold? Well, it's a way of taking a topological manifold and imposing some geometry. So what's geometry? Okay, so what we'll mean by geometry is a pair Gx, maybe I'll divide the board, where X is a manifold, say a smooth manifold, and G is a Lie group, which acts on X by diffeomorphisms. And will require three conditions. One, I want this action to be faithful. Otherwise, just replace G by a quotient. Two, I want the action to be transitive. So in particular, that means that X is a homogeneous space for G. You can think of X as the coset space in G of a Lie subgroup G0, which is the stabilizer in G of some point, and X. Okay. And I want the action to be analytic. In the following sense. If two elements in G, if their action on X agrees on an open subset, let's see, open, non-empty, then they're equal. Okay, so I want the elements of G to be distinguished by what they do on any small open subset of X. Okay. Okay, so examples. We'll come to many examples throughout this course, but just to have something concrete in mind, there's Euclidean geometry. So here, Gx is the isometries of a Euclidean metric on Rn, comma Rn. Okay. And in case this means something to you, the isometries of Rn are, as I think everyone knows, a semidirect product of rotations, the orthogonal group, and translations. Okay, so this is one geometry. And the way that we study geometries is by using the sort of invariant local structure. So it's different. You have to. It can be very different depending on what your pair Gx is. In this case, if you're working with Euclidean geometry, you'd be wise to use the Euclidean metric. So this Gx geometry has an invariant metric, and in fact it's flat. So it's a flat Riemannian metric. Okay. Okay, but Gx geometries don't have to be metric geometries. So just one more example to keep in mind is affine geometry. Here, again, my space X is Rn, and my group is the affine group, the group of affine automorphisms of Rn, where, like Euclidean geometry, there are translations, but now the stabilizer of a point is the full general linear group. And here, we still have some invariant local structure. We just have less. We don't have a flat Riemannian metric, but we do still have a flat connection. So while in Euclidean geometry it makes sense to talk about the distance between 2 points and the angle between 2 lines, that doesn't make sense in affine geometry. But there is a notion of straight lines, and there is a notion of traveling at constant speed along a straight line. I just can't tell you what that speed is. It doesn't make sense to give an actual speed, but I can tell you if you're accelerating or not. Okay. What's not an example? Well, if I take the full diffeomorphism group of Rn, acting on Rn, that satisfies the first two conditions, but not the third. So I can't distinguish two diffeomorphisms of Rn just by what they do on a small open subset. So I don't want to consider anything that large. Okay, here's the main definition. So let's let M be a smooth manifold. Actually, maybe I should do this on another board. Let's see. Okay. So M be a smooth manifold, and Gx a geometry. So a Gx structure on M is and I'll write maximal here, but you can ignore that for a moment, a maximal atlas of charts. Let's see. Okay. Okay, so charts, phi sub u, where u is an open subset of M, and phi u is a diffeomorphism onto its image. Okay, so here's a picture. Here's M. Okay. Here's X. And here's U. So I have some open set here, U. And a map that identifies this open set of M with some open set, diffeomorphically with some open set in X. Okay. So that uses X. How do we use G? Well, we want the transition maps to be elements of G. Okay. So what I mean by that is if I have two different charts that overlap, well, they don't have to agree on the overlap. Okay. But their difference should be the restriction of an element of G. So here's the overlap. Okay. So if I take phi v, phi u inverse, okay, I want this to be the restriction of an element of G to the overlap. So, okay. And in fact, this G is unique if there really is some overlap. This is unique by the analyticity assumption. Yeah.
Is that quite right if the intersection is disconnected?
Okay. Yeah. I'm going to still make this the definition, but you could come up with a definition that might seem not to be equivalent. Yeah. All right. For any two open sets whose union is simply connected and whose intersection is whatever. Yeah. Let's take small open sets, and let's ask that when we look at their overlap, let's ask the restriction to one component of the overlap to be an element of G. Yeah. I do want my open sets to be simply connected. So if you care about that. Okay. All right, so that's the definition. Let me just tell you, I'll say, I use the following terminology sometimes. If M is equipped with a GX structure, then M is called a GX manifold. So if you're looking at a manifold with one GX structure that you've defined on it, you might call that a GX manifold. Sometimes we'll be looking at entire deformation spaces of GX structures, in which case we don't want to think of M as having one GX structure. So we won't use that terminology then. Okay. All right, good. So some basic examples. So the silliest example is that if you have some immersion, a local immersion of M into X, then you get a GX structure on M. For example, here's an annulus. Okay. And maybe X is the plane. Okay. So I can map in my annulus via some complicated local immersion. This defines a GX structure on M. What are the charts? Well, if I just restrict to small enough open sets U, so that the restriction of I to U is a diffeomorphism onto its image, then I can just take my chart to be the immersion. Okay, what are the transition maps? They're just trivial, right? All of the charts actually already agree on the overlap. Okay, so transition maps trivial. Okay, that's kind of silly. It doesn't use G at all, right? So that's not a very interesting GX structure. Okay, so one way to make basic examples of these things is by gluing. So examples that are a little more interesting than the one we just talked about can be made with gluing. So let's just talk about, for example, the geometry, which is the similarities of the plane. So here X is the plane, and G is the group of all similarities of the plane. So transformations of the plane that look like an isometry up to some global scale. Okay. Okay. So what I can do is I can take, for example, an annulus that's embedded in the plane like this, say centered on the origin, and I can glue it. I can glue the inner boundary to the outer boundary with a dilation. So I'm going to glue A along its boundary using the element G, which maps X to lambda X. Okay. Where lambda is the modulus of this annulus. Okay, so topologically, we know that this is a torus, right? This is topologically a copy of the 2 torus, but actually it's a GX 2 torus. It comes equipped with a similarity structure that comes from the way that we made it. So what are the charts? So again, you can use charts. So here's a chart, right? That's a nice open set in M that is naturally embedded in R2. So now the only trick is what do we do with points on the boundary of A? So of course, if we have a point on the boundary of A, we need to make some sort of open set around it, which has a natural map into the plane. And you just do the obvious thing. You glue together two half charts. Okay, so I glue. Yeah. Okay, so if I'm taking some subset of X and gluing it together with elements of G, I should be able to produce a GX structure on the identification space. Okay. Of course, you might say, well, that sounds a little fishy, Jeff. Because yeah, it worked nicely here, but what if you have some complicated polyhedron with lots of lower dimensional strata? There's some things to check. So that's right. So that you can appreciate that, if you haven't seen such things already, I'll give you an exercise. I want to state this well here. Okay. Yeah, so exercise. Okay, so if I take a quadrilateral Q, just any quadrilateral, in R2, and I glue opposite sides, so I glue opposite sides with similarities. Okay, and there's a unique similarity taking any line segment to any other line segment that's orientation preserving. So use the unique similarities that you can use, glue this thing together, and exercise. This defines a similarity structure on the torus. Okay, and of course you're going to do the same thing. You've got charts on the interior that are obvious. You'll glue together half charts along the edges, and the only question is, what do you need to check at the vertex? You need to make sure that you can sort of put together 4 quarter charts in a way that's consistent with the rest of the charts that you've already defined. Okay, great. Questions about that? All right. So, by way of motivation, let me mention some very famous examples from low-dimensional topology. So low-dimensional topology, in particular 2 and 3 manifolds, draw enormously on the subject of locally homogeneous geometric structures. It's actually one of the main ways that people study the topology of low-dimensional manifolds. So in 2D, I'm sure you're all familiar with the following fact. If S is a closed surface, then it admits a GX structure where GX is either, let me write it this way. Let me write it as a homogeneous space. X is G mod G0 is O3 mod O2. That's the sphere. If the Euler characteristic of the surface is positive. O2 semidirect R2 mod O2 that's the Euclidean plane that we already talked about. If the Euler characteristic is 0. And PGL2R mod O2, and that's the hyperbolic plane, if the Euler characteristic is less than 0. Okay. So if you want to study surfaces, you have geometry to use. Any of them will admit one of these 3 geometric structures. And in fact, something like that is also true in 3 dimensions. Maybe I won't write it on the board, but Thurston's geometrization conjecture, which was proved by Perelman, I guess 10 years ago, 15 years ago now, says that, well, if you have a closed 3 manifold, there's 8 special GX geometries, and you can always decompose your 3 manifold in a very specific topological way so that each of the pieces emits one of those 8 geometries. Okay, so that gives a ton of examples of interesting geometric structures on 2- and 3-dimensional manifolds that have been well studied, and we'll talk about some of those a little bit through the course. Okay. Other constructions. Well, you can get GX structures from coverings. If you have a GX structure on M, you can pull that back via covering space, to any covering space. And similarly, quotients. If you have a subgroup gamma in G, it's discrete, and the action on X is free and properly discontinuous, then M equals X mod gamma is naturally a GX manifold. Okay, and so you guys will prove that in the exercises. Intuitively, what are the charts? Well, because the action is free and properly discontinuous, small open sets in X descend diffeomorphically to open sets in M. Those are the charts. Okay. All right, questions? Okay. All right. So all right, now I want to talk about one of the sort of fundamental piece of theory that gives you that correspondence I referred to at the beginning. Okay, so this is due to Ehresmann in, I believe, 1935, who initiated this subject, although it didn't really become, well, anyway, it became more popular when Thurston began using these types of structures to study 3 manifolds. Okay, so let's see. So let's say this. So a GX structure on M determines a pair dev comma hull, where dev is a map from the universal cover m tilde to x. It's a local diffeomorphism called the developing map. Hall is a representation of the fundamental group of M into G. So it's a homomorphism. Called the holonomy representation. Okay? And they satisfy the following equivariance property, that dev applied to gamma little m tilde is Hall of gamma times dev applied to m tilde. For all points m tilde in the universal cover and all elements gamma in pi 1 of m. Okay? And I'll note that these are unique up to an action of G. So I can replace dev Hall with G composed with dev, comma G Hall G inverse. So I replace the developing map with a translate of itself and the holonomy homomorphism by a conjugate. Okay. I'll also note that these determine the GX structure. Okay. All right. So that's the statement. And I'm going a little slower than I thought, so maybe I'll very quickly describe the proof. I want you guys to see the proof if you haven't seen this before. It's important. Because this holonomy representation, this representation that's associated to a GX structure on M is very concrete. It's not very mysterious. Okay, so the proof is essentially, it's just analytic continuation. Okay, so if I take, let's draw a picture. Okay, so here's M. Here's X. So I want to define a developing map. I want to define some sort of consistent synthesis of all the charts into one map. So what do? All right, I'm going to pick a base point, x0, or m0, I guess. And I'm going to take a chart around that point. I'm going to call that u0. Okay, so I've got a little open neighborhood of m0. I've got a chart which identifies that open set with an open set in X. Great. So that looks like the beginnings of a map that I could extend further. So how do I extend it further? Well, I start adding more and more charts and trying to stitch them together. So how do I extend this map to this point over here? Okay. Well, I'm going to choose a path going from m0 to m. It's a compact interval in m. So I'm going to cover it with finitely many of the chart neighborhoods in my atlas. Okay. And okay, so let's call them u1 up to uk. Now, the chart for u1, that's phi u1, it doesn't agree with this chart. So I can't define a map piecewise, but it's okay because I know that they only differ by an element of G. Okay, so if I use the transition map between these two charts, I can stitch this chart to this chart. So this I'll call G01. In general, G I minus 1 I will be phi, will be phi u I minus 1 phi ui inverse. Let me just double check. That's what I want to do here. No. I mean the opposite. Okay, here's what I want. G I minus 1 I phi ui is phi ui minus 1, where that makes sense. Okay, so I make a new chart, which is G01 times this one, and now I can define my map on the union of these two charts, piecewise. And I keep doing that. So the next one goes over here. So what do? I glue it to this chart first with G1, 2, and then I glue both of those. So then I glue both of those onto the base chart, and I keep going. So by doing this, chart by chart, I develop the charts along this path. And what I've defined is a map that's well defined roughly on the union of these charts from M into X, right? Okay, let me write it. Okay, so what is, so I should have named that path. Sigma is a path based at M0. I'll define the developing map applied to this path as, well, G01, G12, gk minus 1k applied to phi uk of the other endpoint of sigma, which in this case is what I called M. Okay? Okay, so what you need to check is that this depends only on the choice of the base chart, U0, phi U0, and that it's independent of homotopy, rel endpoints. So, okay. So I'm going to choose the base chart U0 once and for all. But then as I take paths going into M, I have a choice of what finite covering by charts I use. I want to know that it actually doesn't depend. My construction doesn't depend on that. So you can show that. And I also want to know that, well, if I wiggle my path a little bit, the definition of this map doesn't change. So that's clear for small homotopies. For larger homotopies, you're going to have to start moving charts around. But you can use this. So this will be an exercise. So if you haven't done this before, it's good to think this through and carefully write it down. Okay, and then you see that this is a well-defined map. And what's its domain? It's based paths in M up to homotopy rel endpoints. That's just a way to describe the universal cover of M. And it has image in X. And by construction, it's a local diffeomorphism. When I land in that last chart, UK, if I want to push my path a little further, I can just continue to use that one chart. So the map will look just like UK there, like phi k. Okay, questions about that? Yeah? Okay, what is the holonomy representation? Well, yeah, where does this equivariance property come from? Well, it comes from let's do this. So if I now take a path that first starts with a loop, gamma, sigma was this, right? So if I take a path that starts with gamma and then does sigma, well, what am I going to do? I'm going to have to develop around gamma first. So I'll use the base chart, and then I'll find more charts going around gamma. So this is V0 is the same as U0. This one will be V1, V2, VL. Okay. And then if I look at the definition, the developing map applied to this concatenated path is, where did I write the definition? There. So it's going to be, let me write Hj minus 1 j, phi Vj is phi Vj minus 1. Yeah, it's going to be H01 all the way up to HL minus 1L, G01 up to GK minus 1K, phi UK of gamma dot sigma of 1, but that's just the same thing as sigma of 1. Okay, so in other words, I develop around the charts around gamma, then I use the same charts I had used before to develop along sigma. My instructions tell me to write this down as the definition of the map. And this is exactly the holonomy representation of gamma. Okay? So it's just telling me if I develop around closed loops, based loops in my manifold, and glue all the charts together, what element of G do I get? Okay? Questions about that? It's clear? Okay. All right, let's take a break.